This is the I going. Now, in this circuit, the Z, which is a total impedance, is J omega L plus RS plus 1 over J omega C. Now, if I want to find, which is if I, this is J omega L plus RS minus J over omega C. The value of the I, which is always the voltage divided by the impedance, is going to be this value, the VRS plus J omega L minus J over omega C. Now, if I find the magnitude of this, we haven't discussed in the class how to find the magnitude, but the magnitude of, this is the complex number, is the magnitude of the numerator with the magnitude of the denominator. The magnitude of the denominator, I have a real number and I have a imaginary number in here, so that's going to be a square root of the real number, real part squared, plus the imaginary part, which is this part, squared, which when you do that, that would be omega L minus 1 over omega C squared. Again, remember that the magnitude is a real number. Now, I would like to plot this thing. When we plot the magnitude of this guy, and this is what we end up getting. This is, we're going to get it like a bell-shaped type, and in a bell-shaped type, the maximum is omega naught. Omega naught is the same thing as you've seen before. Omega naught is 1 over the square root of LC, right? So this is going to be the same as you have seen. That's the maximum. But there are 2 points in here which we call the upper 3 dB and lower 3 dB frequencies. So this is omega 2, this is omega 1, and they correspond to half power type. And we're going to find out this thing. These two are the ones that we're going to find out in our experiment. That you notice that the power becomes half, or the magnitude of the initial voltage will reduce to half power. Now, having said that, when I talk about this is not 1/2. This is, we're going to be looking at the RMS values. So the RMS value of the voltage will be reduced by half, not the peak to peak. If you want to do the peak to peak, you got to do a 1 over square root of 2 to convert it to the RMS. All right. So let's get this one. What are the equations for omega 1, omega 2? Omega 1, which is a lower 3 dB frequency. Okay, now I need my notes for that. Omega 1, which is the lower one, minus RS over 2L plus the square root of RS 2L squared plus 1 over LC. Omega 2, which is upper 3 dB frequency, which we're going to find 2L. Again, remember that these are radiant frequencies. So omega is equal to 2 pi f. These are small things you got to remember, because if you're using this equation and comparing to what you're getting with the scope, you got to multiply. You got to divide this thing by 2 pi, because omega is 2 pi f. You got to divide it by 2 pi to get the frequency. So this is RS 2L squared plus 1 over LC. So let's say you get 1,000 in here. I'm just throwing this thing in. So 1,000 is 1,000 radians. So you have to go divide this thing by 2 pi. 1,000 divided by 2 pi. Pi is 3.14156, not 180. So you're going to say 1,000 divided by 2 times 3.14. That gives you the frequency that is, because you see frequency in scope. You don't see radiant frequency, you see hertz. So these are the two. Then the next thing we are interested in is called, what is it, delta omega, which is our bandwidth. Which is omega 2 minus omega 1. Another thing which we are interested in is called a quality factor. Q is quality factor, which is equal to omega L divided by RS. Now what is the quality factor? You see here what you have is basically what we call the filter. The part of the filter that we want, this is the center frequency of the filter. These are the two parts, and the rest of these things you will notice that they become smaller and smaller, and what we call, the word is attenuate. There's attenuations, that means they are going off. For instance, if you look at your FM radio, let's say I'm going to go 101.2. So 101.2 is my center frequency, but if you change your frequency a little bit, go 101.3, you may still hearing the same station. But if you go a little bit higher than that, you don't hear it, and it goes off, or you go hear some other station. So what we want to have is is some sort of bandwidth. This is the effective part of the filter. Now, do we want to have do I want to have a wide bandwidth or a narrow bandwidth? In radios, I want to have what?
A narrow one, right?
Narrow one, because if it's wide, stations, then go over each other, and there will be interferences there. So we do not want to have that kind of things that you're turning and you're hearing two different stations. So Q is a quality factor. That means the higher the Q, the narrower is this bandwidth. So which is we want it for this particular reason. There may be some applications we want a wide bandwidth. But here, for the radio stations, we want to have a narrow bandwidth. You don't want to, so that means we want to have a Q high. We don't want to have Q low. Now, the next part, so this is the part one. So what are we going to do? What you're going to do is you're going to use these formulas, put in all the values that you have calculated there, and find out what omega 1 is. Turn that to a frequency. That gives you the theoretical value of your upper 3 dB, lower 3 dB, and this is your center frequency. We're going to set up this circuit, and we're going to change this. What I'm going to do is I'll probably ask you to do it 1 volt RMS. That's AC in your scope. This is not a DC. It's AC in the scope. So 1 volt RMS, that means, peak to peak, you multiply that by square root of 2, that gives you peak to peak value. So 1 volt RMS or something like that. And then I'm going to start playing with the frequency. You notice that as you change your function generator frequency, when you get to omega naught, that will give you the maximum amplitude. It's like a sinusoid, and it gets maximum, and you increase it, it goes down. You decrease it, it goes down. So it's like that. So if I have so I'm at the omega naught, I have this. If I go higher frequency, this becomes like this. If I go lower frequency, it becomes like this. So as I change the frequency in my function generator, the amplitude changes. I want to know the max, which should be close to omega naught. Then I'm going to go to the 1/2. 1/2 again, I'm using RMS. So if I have 1 volt RMS, I want to change the frequency so that I see 1 volt RMS. When I see 1 volt RMS, I'm going to look at my function generator. That frequency, if I go higher, that frequency should be omega 2. If I go lower, that frequency should be omega 1. We do exact same thing for this one, which is a parallel RLC. The formulas are different, but the procedure is exactly the same thing. Questions? All right, let's do it.
Alright, so for the first part of the experiment, after you set up your thing in series, what you're going to want to do is play with this coarse and fine tuner, and you're looking for the peak. First you're finding omega naught, and that is where the amplitude is the highest. So basically it gets higher, higher, higher as you twist it, and it goes down lower. You're looking for a point down here when it is at its highest. First use the coarse to get it to the around the high point, then use the fine tuner to find the exact height, which should be slow. somewhere around here. Now you go to this RMS value, you look to it, and you divide this by 2. And you're going to do this. You're going to be finding omega 1 and omega 2. To do this, you decide which direction you want to go.
Before you go, record the frequency. That's omega naught. That's experimental omega naught.
Right. The frequency right here, that's your experimental omega naught. Alright, now you're going to want to find your omega 1 and omega 2. And this is done by finding half the RMS, and then turning this to the right first, and then next you're going to be turning it to the left, and you're going to be going to whatever the value of 1/2 that is. And I believe, what was the value? It was 0.7 something.
Yeah, 0.7, let's say 4.
Ours was around 0.74. So right now I'm going to turn this all the way right until this RMS value goes to 0.74. Oh, it looks like it won't go down that low. We're going to do the coarse one first. Okay. Am I going too high?
That's good. That's good.
There we go. So around that. Now you're going to record this frequency. And you're going to do it again. But except going in the opposite direction now. And let's see. So somewhere around there. You're going to record this frequency. The lower frequency will be omega 1, and the higher frequency will be omega 2. Now all you do is switch this into a parallel circuit and follow the same directions.
And use the different equations.
Right, the different equations.